So imagine believing that physics was solved, that the universe worked like clockwork, and then everything started to break down. Welcome to the quantum revolution, and welcome back to the Fundamental Why. I'm Kerry, your co-host on today's episode from Classical to Quantum, the New World.
Yeah, and so I'm your other co-host Sahil, and as Kerry said, we have an episode on quantum mechanics, and this is part one of a two-episode series. So everyone, I would like to make a special announcement today. So we have our guest speaker with us, Kanjin. So I want you guys all to give him a warm welcome. So thank you for being here,
Thank you for
Kanjin.
being here, Khanjan.
Hello.
Thank you for having me. Hello.
Before we start, we just like to ask you a few introductory questions. So I'd first like to ask which university you went to and what's your background?
Sure, yeah. So I currently study at the University of Waterloo. I'm pursuing a Bachelor's of Science in Mathematical Physics under the Faculty of Science. And yeah, I think it's a very awesome program.
Wow, that's amazing.
Great to hear.
Yeah, and then I'd also like to ask about what first sparked your interest in quantum mechanics.
I'm gonna get made fun of for this a little bit, but that's okay. I think that we find inspiration everywhere. And for me, uh, inspiration struck when I was watching Ant-Man and the Wasp.
Oh,
Uh, I thought it was a very silly movie, and they kept saying this quantum thing. And the
Oh,
more I looked into it, the more it aligned with my interests. When I was in high school, I really liked learning about math, physics, computer science, and chemistry. And quantum computing seems like the perfect field to be able to do all of those together. So, yeah.
wow, that's
oh,
an
that's
amazing
great to
yeah,
hear. Yeah,
origin story.
yeah, yes, yeah. Inspiration come from anywhere, really, right? So that's great to hear, Kanchan. And so we'll hear more from you from our discussion section. And so now I just want to give a brief overview of our episode. So we're going to start off by looking at Newtonian mechanics. So what was physics like before, I guess, the quantum revolution, as Kerry mentioned? And then we see a few problems that start to occur that start to I guess, worry physicists. And then finally, the quantum leap. We go to the, I guess, 1900s when physics has radical changes. And along the way, we're going to be exploring some philosophical implications that quantum mechanics has, say, on free will. Okay, so now let's move on to our current proposed theory section. Okay, so first let's start off with Newtonian mechanics. So what does this term really mean? So Newtonian, of course, means coming from Isaac Newton, the man who invented gravity, and mechanics is the study of motion. So I want to kind of paint you a clear picture of what this era looked like. So during this time, I guess the late 1800s, this was where physics was thought to just be complete, right? Newton's equations ruled, I guess you could say. They perfectly predicted planets' orbits, the motion of objects. Everything just seemed to be, complete, nothing else to do, right? And that was the idea there. And it was even said by and even Lord Kelvin had said, there's nothing left to be discovered in physics. All that remains is more and more precise measurement. So physicists really thought it was technological limitations holding them back rather than conceptual ideas. And so to really understand this Newtonian mechanics, right, also known as classical physics, it all hinges on the idea of determinism and how um, every event has a clearly defined clause. Okay, and so let's look at an analogy here. So imagine we have a pool table. Okay, and you let's say you knew all the initial conditions like position, angles, and momentum of of the cue ball, right? Then in principle you could calculate uh, the position of every single other ball for the rest of time. So what have we done here? We've just built out the future, right? Because if let's say our universe was this pool table and each ball was an atom, well, we've just predicted every possible event because everything is made of atoms, right? So that's the idea of determinism, how it says that both the past and the future are set in stone, and the free will is just an illusion under deeper calculations.
And just like my co-host Sahil mentioned, these physicists, they were so confident in their theories and their knowledge that they thought that they basically solved physics. They just needed a bit more technological advancements and theories to bring everything together, and then physics would be solved for good, and we would be able to predict the future. But then one of two catastrophes happened. And this is in relation to black body radiation. So to start, black body, what is it? Well, physicists like to think an ideal black body is an object that absorbs all incident radiation. So you can basically think of it as a pure black object, like a ball, for example. it absorbs all the light coming in, doesn't reflect any of it. And for those of you who don't know, any object that has a temperature will emit electromagnetic radiation, which is basically like light. You can think of it as that. So if you guys know about infrared goggles, for example, if I were to have them on right now and look at Sahil,
Yeah.
he would be in shades of red, orange, yellow, and blue. And that just tells you how much electromagnetic radiation is being emitted in the infrared range. Now, black body radiation just puts the two terms together. It's the radiation emitted by a black body. And so physicists had a beautiful formula, the Rayleigh-Jeans formula, to demonstrate how much radiation is emitted for each wavelength of light. And the Rayleigh-Jeans formula, it was a theoretical formula. It matched experimental results perfectly at very high wavelengths, but something curious happened when you approached lower wavelengths like the UV range. And the Rayleigh-Jeans formula predicted exponential growth
Huh.
in the amount of radiation being emitted. And if you see an actual visual of the graph, it literally ascends to almost infinity, just keeps going up. And obviously, that doesn't make common sense, and it didn't match with experimental results either. So, physicists were stunned. How could they solve such a problem? Their theory didn't match with experimental results at all. And there wasn't just one catastrophe, there was another one. And the other one is called the photoelectric effect. So, for those of you who don't know, this is when light shines onto a metal material, for example, and then the light has energy and it ejects electrons from the surface of the material. And physicists thought that light was a wave. That's what they thought all the way back then in classical mechanics. And if light really was a wave, then the amplitude of the wave, or in other words, the intensity of the light, would mean that the light would carry more energy and would be able to expel more electrons. But physicists did not find that experimental maths theoretical once again. When they shone very bright light, imagine like a very bright flashlight of red light onto a metallic surface, no electrons were emitted. Well, that's because the red light has a very low frequency, and physicists found out that no matter how bright you have or how intense of a light you have, if it's not above a certain frequency, it won't emit any electrons. And conversely, when physicists shone very dim purple light onto a metallic surface, it ejected a lot of electrons, even though it's very dim and it might seem like it doesn't have a lot of energy behind it. And so there were these two catastrophes, the UV catastrophe and the photoelectric effect, that left physicists stunned.
Yeah, and that was a great explanation of the problem. So now I guess physicists have no idea what to do, right? But here's where things get interesting. Here's where the quantum revolution begins, right? So in the 1900s, Max Planck, I guess, comes to the rescue here. He proposes the idea: what if energy is comes in discrete packets, quantized packets known as quanta? That's where the word quantum comes from, right? So what does this really mean? Well, I don't want you to imagine energy as a continuous ramp. But think of a staircase instead. So energy can have certain values, right, on each step, but nothing in between. And that's what quantized means there, right? And so now to really understand what happened, why does this even matter, right? Well, it turns out that this chunkiness math really changed the formula, right? Carrie was saying it went up to infinity, but now once you accounted for this discrete energy idea, it actually fixed all the equations. It perfectly matched observations even at lower frequencies, right? And so now what this tells us is that Max Planck was like surprised, right? How did this happen? It felt more like a mathematical trick, and he never actually believed it, right? And that was how quantum mechanics was born. Well, our story doesn't actually end there. It's just 5 years later that Einstein applies some of these quantum ideas from Max Planck onto light, right? We said that light was a wave, right? That's what it made sense before, but now Einstein was asking, what if light is actually a stream of particles, of packets of energy, which or quanta of energy, right? This new idea of quantum mechanics, right? And so now he called these packets of light photons, right? And so how did this really solve the photoelectric effect problem? Well, I want to also bring up another analogy. Let's say we had a red photon. Okay, you can imagine that as imagine you threw millions of ping pong balls at an electron, right? It's not going to do anything, right? It'll just stay there. But now imagine you have a purple photon. Now you said it was higher frequencies and more energy. And that's equivalent to us shooting a bullet at an electron. So just one bullet does the job, right? So you can see here it's actually the energy that matters more than the, I guess you could say, intensity of the light. That's what physicists were confused before. But now bringing in discrete photons, right? That really helped to fix the problem there. And now this only brings up an even, I guess, more confusing idea. Is light now a wave or a particle? Well, stay tuned for our next episode where we talk about that.
Yeah.
So,
So wonderful explanation by Saho there, and that's basically how physicists solve the two catastrophes and the birth of the new world of the quantum world. And to bring everything back together, I just want to give a more general definition of what quantum mechanics is. And it's basically the study of the motion and interaction of subatomic particles. And it covers a few key concepts, mainly what we talked about, quantization of energy, and also wave-particle duality of light. And of course, many, many more other topics that we'll discuss in our next episode. And one key thing to note is that quantum mechanics says that subatomic particles at the microscopic level, they exist in a state of probabilistic distribution. So they're not definite here or there. And that's something important to note as we move into our philosophy section. So, of course, to start, we're going to talk about interpretations of
yeah.
quantum mechanics and how it leads to free will. So, to start, I'm going to talk about the Copenhagen interpretation, first introduced by Niels Bohr and Heisenberg. And it basically says reality is indeterminate until observed, which basically means there's room for agency and free will. Now, how does this work, you might ask? Well, they basically interpreted it as because quantum particles, they are not here and they're not there. They're different from this microphone per se, where we know for sure it's right here. Quantum particles, they exist in a probabilistic curve, like a wave function. So there's a 50% chance an electron could be here, for example, a 30% chance it could be here, a 5% chance it's like out there. So it's not deterministic per se. And when we observe quantum particles, the wave function collapses into a single outcome. So if, for example, what does observation mean? That basically means interacting with the particle in some way. So if I measure an electron's position, then the wave function collapses and it appears right here, that the electron. And this basically means that reality isn't following a script that was determined from the Big Bang, and we're not the actors in that script. There's free will for us because the universe is governed by this probabilistic outcome, which the outcome depends on our own actions, which promotes our self-agency.
Okay, so yeah, that was a great explanation of the Copenhagen interpretation. And I want to also take a look at a little less popular, I guess, idea and sometimes even controversial interpretation called the hidden variable. So this tells us that quantum mechanics isn't truly random, right? We've talked about it being probabilistic. So the reason why it's not truly random is because we don't have all the information, right? We don't have the hidden variable. And so I always like going back to analogies. So I want you to imagine now, let's say we have a magician who pulls a rabbit out of a hat, right? Oh, that looks like magic, right? How did that happen? But if you were the magician, you would know that there was a hidden compartment under the table, and that makes the magic trick perfectly predictable. So in the same way, um, that knowing that hidden compartment is the hidden variable. So it's almost as if we're the audience who hasn't found the hidden compartment of the universe yet, right? And so everything looks random to us, but in reality, it is predictable if we knew that a certain hidden variable, right? So that's the idea of the hidden variable interpretation. But of course, this hasn't been proven yet. It's also highly theoretical. And I want to move on to just even another interpretation. I think this might seem absurd at first. It's like least popular, I think, of all. It's called the many worlds idea. And it just in the name, you might even wonder many worlds, maybe many universes, a multiverse, right? That is similar. That's actually kind of what it's telling us, right? Because it tells it so many worlds tells us when there's like a quantum event, we make an observation, the universe actually splits into two, and both and all possible, or not just two, but any number of branches, and all possibilities are realized, right? So let's take an example. Let's say I was conducting an experiment. I want to measure where an electron is, right? So electron could be my right or my left. So when I make an observation, the electron has to choose, I guess, a spot, or it needs to be in one spot. So we're going to see that the universe branches, and so let's say in universe one, I measure on the right side, so I see it on the right. I write down that measurement. And then in universe two, there's a copy of me and the electron, and I measure on the left side. So you can see that I won't actually know because the universe kind of branched, right? So I can't interact with my other self who saw the electron somewhere else. So there's this idea that all idea or all outcomes are realized just in separate universes, and that is the many worlds interpretation.
And now, with all of this knowledge armed in our belt, we're going to move into the discussion section next with our guest speaker, Kanjin. So I have the first question for you, Kanjin. So if the universe really is indeterminate, like what quantum mechanics says, does that make us more free or just more random in a sense?
Hmm. I think it would make us more random. Uh, the answer that comes to mind immediately is that if we look at things like probability and Born's rule, we're always in a superposition of many different outcomes. And then whenever we go on to make the measurement, that's when we collapse our wave function or our current state into one of its many probable outcomes. I think for that reason, I want to say it just makes us more random as opposed to more free. My interpretation of that is that, oh, okay, we already have set probabilities to be uh, in one of many states, right? And then, yeah, when you go on to actually make that measurement, you collapse into that.
Yeah, that makes sense. Like the most probable one would also be the one we probably would do. So we don't really get to
Yeah,
choose in
that
that
makes sense.
sense.
Because I guess the main argument for free will that comes from quantum mechanics is that this randomness creates free will because, we're no longer tied towards like calculations, right? Like because, like in Newtonian mechanics, if you just make a certain calculation, you know exactly where something is going to be, like an object, right? But in quantum mechanics, you don't have that certainty anymore. And so some think that gives free will. But at the same time, um, like I'm trying to understand. So how do you think this randomness would not equate to free will, as many like proponents of that idea believe?
Well, so hmm,
Yeah,
I think that free will is something that's incredibly complicated.
exactly.
I don't really have a lot of background for the philosophical side of it. Which is to say that I do think that in randomness you can have some element of free will. Uh, but yeah, if I just look at it from like purely math brain,
Yeah, of course.
I think that it would make it more random. But even then, right? Like, it's not necessarily just that like the most probable outcome would be the outcome that happens
Yeah.
all the time, right? Like if I have like five different states, one of them has probability like 3 out of 5, and the other ones have um like, let's see, we have four left. If we're splitting 2 out of 5 over four, so I guess like 0.5 out of 5, being very bad with my notation, right? Like we can still end up there. And we're depending on, I guess, how you choose to make the measurement, if I was to get extra philosophical, maybe you could end up there. So to some extent, I guess you can recover that free will, but I like to believe in randomness a little bit. I think it makes it a bit more fun. So
Oh, actually,
That's a good argument.
I think that, yeah, actually makes sense. Now I'm kind of also leaning toward that as well. Now that I think about it, because yeah, once you have that element of randomness, it's like you don't have control over that randomness, right? It just happens. So then it's almost as if yeah, we don't have the free will because free will usually equates to like choice, right? So um, yeah, that makes sense, right? Having I guess those
Yeah, so it's
states.
almost like determinism says we follow a script from the universe's beginning to end, and then I guess with quantum mechanics it's the same script but just very like small deviations like every once in a while.
Yeah. And also, I'm just gonna throw a speculative idea out there. But we don't even fully understand the nature of quantum mechanics, right? Like there's potential like for it to like be a hidden variable. Although many experiments have proven that false. Like we're always learning new things, right? So like in our current view, quantum mechanics is probabilistic, but there's always that. I guess in the future we might find that um, just like how quantum mechanics had overturned Newtonian mechanics, maybe something will overturn quantum mechanics and might bring back determinism. But at least for now, in a probabilistic perspective, we shouldn't like necessarily conclude free will just due to randomness, right? Randomness just can happen. Any outcome can happen, and that's just yeah due to randomness and nothing like none that doesn't have to do with our control, right? So yeah, I like I guess your argument there, and that makes sense. Yeah, so. Yeah, that was a great question. So, I guess yeah. Now I want to move on to I guess our next question. This is more of I guess a personal question for you now, Kanjin. Given like your background, right, taking mathematical physics and being in the Institute for Quantum Computing, I want to hear like what are your thoughts on what did you find as the most counterintuitive part of quantum mechanics when you first learned it? So
Hmm. For me, when I was first learning quantum mechanics, I'd definitely say spin. The spin-based approach to quantum mechanics was the most counterintuitive for me. Uh, that approach requires a very solid foundation in linear algebra, and although I had that, I kind of underestimated just how much I needed to know. Um, yeah. So spin is one of the things that you is intrinsic about a quantum system. You can have different types of spins, like spin one half, spin three
yeah,
halves, so on and so forth. And a lot of the intuition and math that follows with that was just so tricky for me. Now I think I can handle it a little bit better. And also because now I've learned about the other approach towards quantum mechanics as well, which involves a bit more calculus. That's the one that they cover in a book such as David J. Griffiths' quantum mechanics book, whereas spins would be an approach that the McIntyre book would take towards quantum mechanics. Beyond that, I guess just navigating a lot of the more popular ways to explain quantum mechanics was also a little bit counterintuitive to me, saying that, oh, okay, no one's been able to rederive the Schrodinger equation since Schrodinger came up with it. And
yeah,
then, like 2 Thursdays ago, we derived it in class from fairly straightforward principles.
yeah,
Things like that. Like a lot of like the quantum mysticism, I'd say, has been hard to navigate. And then because that was what I got into the field with, it's been a bit counterintuitive to see like, oh, okay, people have told me this of like, oh, okay, no one understands quantum mechanics. It's a very hard field.
yeah,
But at the same time, we've had very talented people working on it for over 100 years, right? And with that, we have built some understanding. It sure there's a lot of quantum mechanics that's like very, very tricky, but we do have talented people that are working on it that have been working on it for like hundreds of 100 years. And now we have people working on explaining it better to the general public as well. And that's part of what my work at the IQC was like of, oh, okay, I have all this like textbook knowledge and I want other people to be able to have it in an approachable way. So how can I talk about things like entanglement, superposition, so that it
yeah.
doesn't seem as foreign, but it also doesn't seem, it's also like not compromising on how complex of a topic that.
Wow.
Oh,
Okay.
well, that's
Yeah, I guess you,
great
you
to
said a
hear.
lot
Yeah,
in
basically,
that, and I kind of agree with you. Yeah, I feel like going back to the beginning of what you said, like spin. I feel like even right now, I of course I haven't even gone to university yet, so I feel like this idea of spin. I've heard like, a little bit about it, right? And it does like I feel like the reason it's counterintuitive is because you could actually just imagine it as like let's say an electron is like a ball and then it's like spinning, right? But that's not the actual way it works, right? Because the way you define spin, because electrons like are usually like a point like particles, right? So like spinning happens about a point. So how do you have a point spinning on itself, right? Like that's like that kind of doesn't make sense, but I'm sure like yeah, as I kind of go into university, that idea will probably make a bit more sense. But yeah, that the spin also the fact that the spin can, as I said, it's also in superposition, so you can have like two spins, kind of right.
spinning
Like imagine
opposite
spinning up and
directions.
down
Yeah.
at the same time, right? So like that also like just the fact that when you combine probability with spin, then it becomes like, even more like counterintuitive there, right? And yeah, so that makes sense. And also, what you talked about, how um, a part of your work is like to make quantum mechanics more engaging to the public, right? And I think that's something I feel like because quantum mechanics is at like the top of the most abstract for physics, right? Like it's at the subatomic world, and the only reason it's so abstract is because we don't live in the quantum world. We live in
Yeah,
our
we
regular
live
world,
in
right?
like a
So
cause and effect
yeah,
thing.
we build our intuition around like a ball falling down, but not an electron, I guess, moving, right? So it just that's what naturally makes it much more complex, right? And so that's why I think the outreach efforts are very important. I think to make this field more accessible to the general public, right?
Yeah. I also greatly admire the work you're doing because there's like a lot of like random floating knowledge that may not be
Mm,
100% correct going around. So a lot of people who don't know about quantum mechanics have like wrong perceptions about
exactly.
it because of that like wrong information there. Mm.
Yeah, so a lot of misinformation can go on around just like you said, Gary. So it's important that we kind of clarify these concepts. But at the same time, yeah, you need to simplify it in a way that does not like, make the concept make it incorrect, right? It should still be accurate but simplify. And that finding that balance is very difficult, I guess, right? Sometimes. So yeah. So that was, I guess.
Yeah. And I have another interesting question. So I know a lot of people find the topic of superposition a little bit counterintuitive because how can something be in like multiple states at the same time? So I was just curious if you had a better way to explain
Explain that, yeah.
superposition or to make it more easier to understand for other people.
So the way I like to explain it, and it is still something I'm workshopping, I think, yeah, I've iterated on it quite a bit, but it's okay. If I'm let's say I'm like half asleep, half awake. You know that one state you're in where like you're not fully, it's, I guess like a lucid dream sort of situation.
Yeah.
And then my alarm goes off. We can think of the alarm as like the measurement, and because I'm half asleep and half awake, I'm in that superposition state. Once my alarm goes off, I'm either going to sleep through it or I'm going to stay awake. I'm
Yeah.
going to go into one or the other as opposed to just like in between both of them. Yeah.
Oh, wait, that's
Yeah,
actually a
I
great
like that analogy,
analogy.
actually.
Yeah,
That's a
yeah.
great way of explaining it, right? Yeah. It's like, yeah.
I find that this tends to resonate really well with like students because we're all incredibly tired.
Yeah,
Oh,
exactly. Yeah, because
sleep
we
deprived,
also sleep
deprived.
in sometimes.
Hmm.
So yeah, okay. So yeah, that's so. I guess this was like a great discussion we had, Kanjin, and now let's move on to I guess our conclusion where we kind of wrap up. So now for I want to kind of just give like a brief summary of what we've spoken about today. So we talked about Newtonian mechanics, understanding those ideas, and classical physics and how everyone thought physics was complete. Then we move on to I guess some of the cracks and the problems that appear. Right, and Kerry mentioned black body radiation and UV catastrophe, right, as well as the photoelectric effect. And then last we kind of conclude with the we conclude by looking at some of like the solutions, right? How quantum mechanics fixed it with this discrete idea for energy, and we also along the way we look at philosophical implications like for free will, and like the three different interpretations like Copenhagen, hidden variable, and then now for our discussion section, we spoke with Khanjan about his thoughts on the most counterintuitive aspect of physics being spin and the importance of outreach efforts there, as well as how in terms of quantum mechanics and free will, it doesn't necessarily guarantee free will due to randomness.
Yeah, so we've been talking about all kinds of questions and we've been answering them as well. And now we'd like to ask you guys, the audience, one final question. So, do you believe that quantum mechanics and indeterminism grants us free will, or does it just replace one kind of unpredictability with another? So, three choices to answer. We either have A, yes, it does grant us free will. B, it just makes everything more random, so no, it doesn't grant us free will at all. Or C, there's a more complicated answer to that. And we'll dive into that in the
Yes.
next episode as well. So, to end off, we'd like to
Yeah.
thank our
Thank you
guest
so much.
speaker,
Yeah.
Kanjin.
Yeah.
Thank you so much
Khanjan
for
for
coming on.
joining us. So yeah, it was a pleasure to like speak with you on
Yeah,
this topic and gain your insights here.
yeah,
So
we greatly value your time and
yeah.
your valuable insight. So make sure to tune in to our next episode where part two of our series, we're
Series
going to
on
go
quantum
over more
mechanics.
advanced topics. And everyone be sure to
To like
like
and
and
subscribe.
subscribe
Yeah.
and
See
see
you
you all
all
next
next time.
time.